I came across this question a while ago and I thought it was very interesting. I want to share it with you. It's a paper one question, so there is no calculator. We're going to see what types of things we can do for sketching of an unfamiliar function, even if we don't have a calculator with us, okay? So obviously this is an IB question, so it had a part A, B, C that had to do a bunch of specific stuff, and then sketch the graph of the function was the last item on the question, okay? But I'm not gonna make explicit reference to those things as I'm solving the question because, as usual, like most of the time, these parts A, B, C, they are not disconnected things, okay? They don't just want you to do a bunch of random things with the function. If they're asking you to do those things and then the last item is sketch it, it's because doing those things will help you sketch the graph of the function. But I'm not gonna go through exactly what the parts were because I don't remember and because they were pretty obvious. When you're asked to sketch a graph of any function, you have to consider what are the relevant features of functions. So yeah, the parts of this question were guiding you to find these things, and that's why I said they're obvious, because you don't really need to be reminded that you're supposed to find a turning point, for example, because these are things that you're supposed to indicate on any graph of any function that you're sketching. So let's see what we can do about that. Asymptotes. There are vertical asymptotes and horizontal asymptotes. So what is this function doing? Well, clearly, it's going to have at least a vertical asymptote because you can't divide by 0. And x equals 0, well, I technically shouldn't even have included that in the domain of a function, right? 0 is not in the domain of the function, but it is right there. Everybody that is after 0 is in the domain of the function. And this function clearly has at least a vertical asymptote. There's two reasons for that, actually. The other reason is that if you look at the numerator of the function, it's log of x. So log of x is a familiar function. We know that ln x looks like that, so it already has an asymptote at x equals 0. 1 over x also has a vertical asymptote at x equals 0, so that's every reason to know this. Let me write it on the list. I'm not going to worry about asking myself whether it has a horizontal asymptote right now, because the answer to that is going to become clear. And I always think that it is a good strategy to just do the things that you find easier straight up. Okay, so don't waste time thinking about the details that you're not sure about. Just write down the things that you are sure about. That's a good way to get started on the question and have something on the page to make you feel more confident, even though it may not be everything, but you've at least done the parts that you're confident about. And right now we're very confident with that vertical asymptote. So let's go ahead and think about x's intercepts. Well, of course, it's not going to have any y-intercept because that would be an f of 0, and 0 is not in the domain of the function. So now we have to ask ourselves about the x-intercepts of this function, and finding x-intercept is always about answering the question, when is the function equal to 0? That's what I'm going to ask. And a fraction is only going to be equal to 0 when the numerator is equal to 0, right? So the next step is just ln x equals 0. The denominator actually doesn't play any more role in setting this equal to 0, right? It's just the numerator. Please don't get confused about that. And if you want to think about this in terms of what operation happened to both sides of the equation, the operation was multiplying by x to the power of 4. Which on this side cancels the denominator, and on that side nothing happens because it was 0 times something, which is still 0. Well, now we have to remember, who is the value of x whose log is 0? Well, this is something that you're supposed to know by heart. The x is going to be 1. But if you don't remember it at the time, you can still find it by just using the definition of log. Remember that ln is log base e. So you're going to switch it around and say that x is equal to e to the power of 0, and anything to the power of 0 is 1. So I've already put that on the list. There is an x's intercept at x equals 1. It's the only one, right? because there are no other solutions to this equation. But maybe at this point you want to ask something a little bit more. And this is a part where I remember specifically that the question was asking you to do it, okay? One of the items in the question asked you to see where the function was bigger than 0. So it was guiding you into looking at it as an inequality to find out a little bit more, okay? That's not going to be too difficult to change in this part here, because check it out. The operation that I did here was multiplying by x to the power 4. 4 is an even number, and x was positive anyway. So this is a positive number that I'm multiplying by. That means that I don't change the sign of the inequality. And now I have to think a little bit. I really do need to think a little bit here about whether this sign will change or not, because what is the operation that I am doing on both sides of the equation here? It is the inverse operation of ln, which means that from this line to this line, I am taking the side of the equation and putting it as an exponent of e. Okay, so it's e to power of the side. This is the operation that I'm doing on both sides of the equation here. And e to the power of x is an increasing function. E to the power of x looks like that. So this does not change the sign of an inequality. Probably there's other arguments that you could have used to figure this out, okay? But I like this idea of doing the increasing and the decreasing functions to see whether or not you should change the sign of an inequality. So that's my favorite. That's how I did it. So the conclusion is that our function f of x is bigger than 0 to the right side of that x's intercept that we found there. So we can put that in the list somehow. There, I've drawn a little bit of an axis with an orange bit of function going up, right? So it's negative on the left and positive on the right, which is what we just found out here. Next, we have to talk about turning points. And in order to find turning points, we need to take the derivative of the function, because the turning points are going to be the points where the tangent line is horizontal, right? So we're going to be looking for f prime equals 0. First, we need to take the derivative of this function. It's a fraction, so it's a quotient. We're going to need to use the quotient rule. Here is the quotient rule. So the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, everything over denominator squared. Please write it out like this. Resist the temptation of doing cancellations as you're writing it down. Like, I know 1 over x times x to the power of 4 is x to the power of 3. But I really do recommend you write it out like this in the first line and then do the cancellations later, okay? So that's how you show the examiner that you really know all the steps. Now I've done all the simplification that I could, and this is the derivative of the function. What I want right now is to find the turning point, which means that I need to put this thing equal to 0 and then solve that equation. So let's do it. There you go. X is equal to e to the power of 1 over 4. Now, I don't know about you, but a lot of my students, when they get to something like 1 over 4, they can't resist the temptation to write it equals 0.25. I really don't think that's a good idea. I mean, it can be a good idea in sometimes when you're going to do some further calculations that become easier as decimals. But that's definitely not the case, because what we're going to do with this number is to put it in the exponent of the irrational number e, which you're not even required to know a precise value for anyway. Remember, this is a paper 1 question, so it's not about knowing that e equals 2 point whatever. I don't even know it. So I would leave it like that. We could also use this to find out when the function is increasing or decreasing, which is a nice way to check if the critical point that we have found is actually a local maximum or local minimum. Is it even a turning point? So we could do that. It would be a process very similar to what we did before to find where it's positive and negative. we're just going to ask where is this bigger than 0, because then the derivative being positive is when the function is increasing. So now we're asking for increasing function, multiply both sides by x to the power of 5, which is positive, so it doesn't change this sign. Then I added 4 ln x, that also doesn't change the sign. Now I divided by 4, which is a positive number, so it doesn't change the sign, but be careful because I've also flipped it around, okay? I switched left and right. So this is this way. And now I am doing e to the power of the sides of the equation, just like I did before. So that's an increasing function, does not change the sign of the inequality. So there you go. It is increasing for x smaller than this value, decreasing for x bigger than this value. It's increasing before, and it's decreasing after that, so that makes it a local maximum. All right, so maybe it's time to put all that together and try to sketch the graph of the function like we wanted. I'm going to start by marking the x-intercept. So we have an x-intercept here where x equals 1. And now I'm going to put the vertical asymptote at x equals 0. And I have drawn the vertical asymptote going down instead of going up because at some point I did calculate when the function was positive and when the function was negative. It's right there. So it's supposed to be negative to the left of 1, right? So that's why it's going down. Well, now it has to go up. Here's the thing. E to the power of 1 over 4 is not really a number that I know precise digits for, right? So in terms of doing a sketch, it doesn't really matter if I put it too big or too small because the scales of the axis don't matter when you're doing a sketch versus a drawing. But one thing that does matter is that everything needs to be correct with respect to the other things, right? So I have a 1 here, and now I'm going to put a second number, e to the power of 1 over 4. If that's bigger than 1 and I put it to the left, that's bad. Yeah, I can't do that. So, but the shape of the function that I have so far is telling me that that number needs to be bigger than 1 because that number is going to be a local maximum. So there's no way to have it down here, right? It's going to be like this. Now, maybe it's worth talking a little bit about how am I so sure that we couldn't have a local maximum to the left of 1? Because I drew the asymptote like this just because I wanted to. It was the simplest thing. But who said that it couldn't do this? You know, so that is a local maximum right there. But the thing is that that kind of thing, that kind of shape for this function is not going to work because if I put a local maximum here in a weird place, I have also created a local minimum, which I know there isn't any in this function because when I was calculating turning points, I only found one answer, so I can't have that. I know this example may have seemed silly. Nobody was really thinking that the local maximum would be there, but I like this idea of thinking about the things that are not possible to put the pieces together, because sometimes that is going to be the way that you figure out what else is there. So what is possible? If nothing else is possible because I've explored the possibilities and there's no way to make them fit, then whatever is left is what needs to be happening in the actual situation. So for example, right now it feels like I've already put all of my calculations into the sketch, but the sketch is not really finished. I'm not saying what's happening over here. So let's consider options. Can the function go up? Well, no, it can't, because that would make a local minimum here that we've already calculated doesn't exist. That maximum is the only turning point, so this doesn't happen. Can the function go down like this? Well, no, it can't, because then you would have another x-intercept here, which we've already calculated way in the beginning. Doesn't exist. The x equals 1 is the only x-intercept in this function. So it can't go down either. Well, but if the function can't go up and it can't go down, what else is it going to do? Well, it does go down. It just can't cross the axis, right? It goes down because it's a decreasing function at this part. So it is going down, but it can't cross the axis. And that's how I find out that this function has an asymptote. It also has a horizontal asymptote. The way in the beginning of the question, I was like, let's not worry about that because the answer will make itself clear later. This is what I was talking about. Now, it is true that we didn't calculate enough stuff to make sure that the asymptote is actually at y equals 0, which it is. We just know that it has to level out at some point between the maximum value and the x-axis. Okay, that's technically all that we have right now, even though, trust me, the asymptote is at y equals 0. I also don't think that the question was assigning any marks to that. I think that because you're not really able to tell it right now, then any asymptote that you drew here, I think, would be considered fine. Another thing that we could still put on the list of relevant features to include in any sketch is inflection points. But the reason why I'm putting that in a different color is because I think it's not as common to be required to include inflection points in a sketch as it is for the other features that I mentioned here, okay? But let's try to do it for this one. And an inflection point is the point where the function changes concavity, right? So you have concavity down, you have concavity up, and the point where that changes is the inflection point. We know that concavity down is when the second derivative is less than 0. Concavity up is when the second derivative is bigger than 0. So the inflection point is the point where the second derivative changes sign. You can search for f double prime equals 0, but of course you have to sometimes check if that's actually a change in concavity. So we are going to do the second derivative here because that's an important part of this process, but also, and this is what I actually wanted to mention for the purposes of this video, okay? It doesn't even really matter if we're going to actually be able to calculate it or not, because I don't know how difficult that is going to become. But what I wanted to show you is that with everything that we have so far, it is clear that we do have one inflection point and where it is. Because that was not done intentionally because I wasn't even thinking about concavity, but it's a consequence of all of the other things that I was having to do when I did this sketch. So check it out. Over here, I have a local maximum, which is naturally concavity down. But over here, in the end, we have a horizontal asymptote that is coming from the top. So it has to be slowing down to 0. So this derivative here is negative, but it's increasing towards 0. So you see, there is no way to fit all of these features of the function without an inflection point in the middle. And that is really what I wanted to point out, because we're talking about how to construct interesting graphs without the help of a calculator, but knowing all of the things that we know about how to calculate relevant features of the function. And this, I think, is a very interesting consequence, right? If you're going from this local maximum here, concavity down, you're ending in a horizontal asymptote that has concavity up. So you can see that there is an inflection point somewhere there. But I am going to have to calculate the derivative of this function and then set it equal to 0. So I'm not really sure if that's going to turn into an equation that I want to solve, but let's give it a try. So once again, I've had to use the quotient rule. Here is minus 4 over x is the derivative of the numerator times x5 the denominator, and then minus the numerator multiplied by the derivative of the denominator over the denominator squared. That's just the quotient rule again. And I'm going to do any simplification just like I did on the other one. Okay, so that's not so bad. It looks very similar to the other one. Let's just do the distributive of this 5 over here, which got us a positive sign here because it was minus with minus. And then we have minus 4 minus 5, which is going to be minus 9. Now we want to put that equal to 0. And solving this equation is also very similar to another one that we did earlier in the video. We start by multiplying both sides by the x to the power of 6 to get rid of the fraction. And then we added 9, we divided by 20. Now the only step left is to use the exponential to get rid of this ln, and the answer turns out to be e to the power of 9 over 20, which is another one of those numbers that may look a little bit ugly. We don't have precise digits for it, but then again, we don't need them. We don't even need to be able to compare whether this one or that one is bigger or smaller, because that is implicit in the picture, where clearly e to the 9 over 20 needs to be bigger than e to the 1 over 4, because that's just the way that the shape of the function looks. Now, as a general tip for sketching, anytime that I mark an inflection point on a graph, I like to draw the tangent line at that inflection point. I think that just adds a little bit of certainty that I really, as a student solving the question, that I really know what an inflection point means. Because a consequence of the fact that the concavity is switching there is that we have something special happening with the tangent line. Because at points where the concavity is up, like this one, the tangent line is all under the function. And on the other hand, at points where the concavity is down, like this, if you draw a tangent line, you get it always above the function. So what happens in the inflection point is that each side is going to do one of those things. So the tangent line is going to be crossing the function. It's kind of here, more or less. And then visually, I estimate where it makes sense to draw a tangent line that is crossing the function. But it's not any crossing line. It has to be crossing in the appropriate way. It's crossing, so it went from the bottom up, but it is still tangent, okay? You can't cross it like this, for example, where it makes an angle with the function. That would be wrong. So that's what I want to show in the function that we're actually sketching. So there you go. I've drawn the tangent line in a dashed way here. There is like maybe one more thing that I would do to make it even more complete, is that these two interesting points here, currently I have their x coordinates, but I don't have their y coordinates. So if you want to do that to be super complete, it's not that difficult. All that you need to do is plug in these numbers into the definition of the original function to see what number comes up. It looks a little bit messy because the numbers are ugly and some people get nervous when the numbers that they're working with are not like 2, 3, but rather something like e to the power of 9 over 20. So it looks messy, but it's actually not that bad. It's ln of e to the something, so there are simplifications that we can do here. There is a 1 over 4 to the power of 4, so those exponents are going to multiply each other. It's going to become prettier. Well, the first one is certainly prettier than the second one, but anyway, it's the same kind of simplifications that's going on. So there are the numbers on the graph, and now there's literally nothing else that I can think of to do with this function if you ask me to just sketch it, okay? Now, I think it's a very good thing that the question has parts A, B, C, D, like I mentioned before, because then they make it clear to you exactly how far they actually want you to take it. I don't exactly remember what the items were, but I'm pretty sure that plotting the inflection point was not a part of it. I don't remember having seen that number when I solved this question. So I don't know, I may be wrong. So yeah, it's very nice that they guide you through how much you actually have to do so that you don't waste time doing a bunch of things that are unnecessary, which might totally happen if they just ask you to sketch it. I would do all of these things and maybe I don't have to. So to be absolutely 100% complete in this graph, there is one thing that I mentioned earlier that I wasn't really doing, which was to prove that the horizontal asymptote is at y equals 0. I said that there must be one, that it's somewhere around here, and also that you probably don't lose marks for drawing it wrong. But I want to prove that it actually is 0, and that limit up there is what I need to calculate in order to do that. Okay, so hopefully that's equal to 0. And if you are a HL student, you may recognize what is going on here. This is a situation where when x is going to infinity, both the numerator and the denominator are going to infinity. So this is exactly the type of situation where we can use L'Hopital's rule. It's either 0 over 0 or infinity over infinity, which is this case, right? So in order to use L'Hopital's rule, you can take the derivative of the numerator and the denominator. That is not the quotient rule. I want to make this perfectly clear. If you're an SL student watching this, maybe skip this part so that you don't mix up two things that you don't even need to know this one. The quotient rule is still the way that I did it earlier in the video, which is when I'm trying to take the derivative of a function. But right here, I am not trying to take the derivative of this function. I am trying to calculate a limit of it when x goes to infinity. And I find myself in a very specific situation, which is if I just plug it in, I will find infinity over infinity, which I then can use L'Hopital's rule, which is also very specific. It's not taking the derivative of the function. It's what I've done here. It's take the derivative of the numerator and the denominator separately. So now let's organize that a little bit. And that limit is very clearly 0, like we wanted it to be. Okay? But I'm interested in showing you, is there any other way that I could have done that without going through L'Hopital's rule? And this is absolutely just for the fun of it, okay? I like exploring different ways that we can do things. Of course, when solving a question in an exam, you don't need to do it in multiple ways. You choose your favorite. But in order to even have a favorite, you need to know more than one, right? So that's why I like doing and redoing things over and over again. My point is not to finish the question. The question has finished a while ago. So, by the way, speaking of this, when we decided that e to the power of 1 over 4 was really a local maximum, we did that by calculating where the derivative was positive and negative. But there was a different way that we could have done that, since at some other time we did calculate the second derivative when we were looking for this one. So we already had the second derivative in our hand. It would be very easy to use the second derivative test to figure out whether this critical point was a maximum or a minimum, right? You just take the e to the power of 1 over 4, plug it into f double prime, and that's going to be a negative number, which tells you that the concavity is down. So let's think about this for a little bit. I don't want to use L'Hopital's rule, and I still want to get to kind of the same conclusion. So what I'm thinking here is that it's much easier to work with x to the power of something than it is to work with ln. So my intention is to show that ln of x is always less than x, so that I can maybe substitute this one for that one over there, get to an easier limit of x over x to the power of 4, which is clearly 0. Let me write that out. That's what I'm trying to do here. That's my plan. Okay, of course, I still need to show that this is actually true, but if it is, then this fraction is also smaller than that fraction. That fraction is a lot easier to work with because it's just this, and the limit at infinity is 0. So I'm going to try to show that using another sketch. Here is the very easy graph of the function y equals x, and now I'm going to compare that to the graph of y equals ln x. I've drawn the easy part here, which is between 0 and 1. It has this vertical asymptote, so it's still negative. So it's obviously smaller than the other one that is positive, right? But the problem is that as I go after 1, it's easy for me to do this and say, well, look at that. Ln x is always smaller than the other green function, which is x. But I'm cheating, right? Because I drew it this way because it was convenient to me. I wanted to be below the other function. I don't at this point have enough information to say that it's always going to be under the green function. Maybe it went up in a different way than I was drawing. Like maybe it did this, for example. See, it still looks like the ln function that we know. It still has the vertical asymptote down here. It still crosses the x-axis at 1. It still keeps going up, but with this concavity down sort of look. But now it's crossing my x function. So how am I going to decide which one is the truth? Again, without access to a calculator. So my plan now is to make more use of the one point that I know everything about, this point right here. Obviously, at this point, it is below the other function because its value is 0, where the other one is 1. But I don't want to look just at where the functions are right now. I want to also look at how fast they are growing, which is looking at their derivatives. And if it turns out that the red one is not only below the green one, but it's also growing slower than the green one, then it's never going to catch up because it doesn't have enough speed. So let's do this. Let's treat both of these things as functions, take their derivatives, and compare. Those are two very easy derivatives to take. The derivative of x is just 1, and the derivative of ln is 1 over x. And I'm really interested in what happens for x bigger than 1, because this other part here, one is negative and the other is positive, so it's obvious. Now, what I want to see is what happens for x bigger than 1. And the conclusion is very natural. For x is bigger than 1, 1 over x is less than 1. So this derivative is smaller than this one. The red function is growing slower than the green function, so it cannot catch up. So the final comment that I want to make to wrap up this video is about what would change if this question was a paper 2, if we actually had access to a graphic calculator while we're doing that. So I've traced the graph of the function here, as you can see, and I think this graph is a little bit disappointing because you can see that it kind of has the same shape. It has the vertical asymptote and the horizontal asymptote. But that middle part there, which is really interesting, where we see the local maximum and then the inflection point, that is very small. Of course, that is because of the window that I chose, which is always a big part of making a good sketch with the calculator. So I'm going to show you a few different windows that I tried, but none of them look really good, in my opinion. I'll show you why. Well, first of all, this one, besides having the middle part very small, it still is not really showing the vertical asymptote in the way that I wanted it to show. Because we know that that vertical asymptote is at x equals 0, right? And that's not what it looks like here. It looks, of course, like it has a vertical asymptote, but if you told me that that vertical asymptote was at 0.4, like I am showing in this other picture here, I would believe you just by looking at the picture. Of course, not if I look at the formula for the function. I know that it has to be x equals 0, but just by looking at the graph, if you told me that it was 0.4, which is that vertical line that I have traced there, there's nothing to tell me that that's not correct. And I think that that is the big problem when we do this kind of thing with a calculator. We kind of get the feeling that it's going to be easier. And of course, it's good to have the calculator there so that we can check if what we're doing is correct, right? But there is this very big risk of us just trusting the image in the calculator too much. So if you were to just look at the picture, you could assume that the vertical asymptote was somewhere at around x equals 0.4, because visually that's what it looks like, but that's wrong. So be careful not to make that mistake. if you're using a calculator. Okay, just use it for checking, but don't rely visually 100% on what you're seeing. Just because there is an asymptote at x equals 0 doesn't mean that we're going to get there anytime soon. It may take a long time, which this function is apparently a very good example of. I'm already at like -50 or something, and it still looks pretty much like it's not going to go past 0.4, but we know that it does. I didn't really go to the trouble of going down even more to see like how far would we have to go down to see it getting to 0.1, for example. Maybe that's something that you can try to do if you trace it using different windows. Instead, I've zoomed out a lot for this next picture, which is what we would need to do if we want to see both the horizontal axis, y equals 0, and in the same picture, we want to see down enough that the vertical asymptote actually crosses that 0.4. But then we have to zoom out a lot in order to do that. And of course, when we zoom out, we lose sight even more of the local maximum that we were barely seeing before, and now it's just invisible. So here I did the opposite. I zoomed in around the local maximum so that we can see it a little bit more. And still, the local maximum and the inflection point still look kind of disappointing, even though I can't see them. So on this one, I've stretched the horizontal axis differently than the vertical axis so that we can see a little bit more of that shape that goes like this, so that it doesn't look very flat all the way around the inflection point like it was looking in the other picture. So I zoomed in even more for this one so that it felt like there was even a point in tracing a tangent line. And this is the best window that I could get, I think. So it's the one that more closely resembles the stuff that we did by hand. But still, the vertical asymptote is not looking good. So I think that's the takeaway from all of this. If you have the calculator, it can feel like it's easier, but then again, it might be even more difficult because there may not be a window that is good for all of the relevant features of the function at the same time. There's a window that's good to see the asymptotes. There's a different window that is good to focus on the turning point. And that's pretty much always the case. So that is the advantage of trying to do a sketch versus a drawing, because then you don't have to choose a fixed scale for either of your axes. You can just choose to sketch it in the most appropriate way to highlight each of the relevant features of the function. So you know that the difference between when they ask you to sketch or to draw is this, right? That when they say sketch, you don't have to make an accurate scale on your axis. But some people do think that, well, even though it's not required, surely it must be better if I do an accurate scale. And that is not the case, okay? Because if you're trying to do everything accurate, then you're not focusing on all the relevant features that you should be focusing on in the sketch. So that's it. Bye.